Today we'll start with the Newton's method. This is a topic which will not show up in the exam, so listen carefully. This is one of the most interesting parts. Okay, relax and just enjoy. Okay, so Newton's method is for finding numerical solutions. So what do we use this? This is to numerically approximate a solution to f of x equals 0. Okay, so there are several ways of doing this. In most of these methods, you start with the healthy guess, and then using your guess, you calculate something which gives you your second guess. Using that, you feed it into your formula, you obtain another guess. Okay, so if you are lucky, if you are lucky and if your first guess was a lucky guess, the sequence converges to one of the roots. Okay. So the picture here explains what will happen. So we have, suppose we have the graph of the function like this. And a typical picture will be something like this. So this is y equals f of x. So you make a healthy guess. So let's say this is the point we are trying to find numerically. Okay. So you guess that probably the number is somewhere here. Okay. So this is your first guess. Your first guess. So what you do is you take this point and you come to this point, x sub 0, f of x sub 0. Okay? So make a guess, make an educated guess. X sub 0. Okay? So you calculate that f of x sub 0 is not 0, so you want to do something. Write an equation for the tangent plane to y equals f of x at the point x sub 0, f of x sub 0. Okay, so this is your first thing to do. This is your second duty. Okay, so you draw a tangent line. Okay, so this is your tangent line to y equals f of x at x sub 0, y sub 0. Okay, it intersects, you see the x-axis at a point closer to the actual root. Okay, so this is the ideal situation. This doesn't always happen. Okay, so for example, if I made for my first choice here, I take this point, you see the tangent line intersects the point here. Okay, so there are always some dangers here, but then life is full of dangers. So you take this point as your second guess. X sub 1, your second guess. Okay, so the equation of this, and you write the equation of this, find the point where this tangent intersects x-axis. Okay, so this point is your second guess, and repeat. Okay, so you come to this point now. Okay, so this point is x1, f of x1. You draw a tangent line there. Okay. So this is the second tangent. So this is your next guess, x2. So you see in this nice situation, so you are always hoping that you will land in such a part of the graph, because the graph will be different like this. It has different parts. So you roughly plot the graph. You, you find a piece like this. So you start hunting for this thing. Okay? So you see that this approaches to this point quite fast. And at some point, you say enough is enough. So generally, you are calculating this on a computer. You write a one-line program, and it keeps doing this. So you check the numbers. After a while, the number stabilizes, because now the difference is beyond the number of digits you allowed. So if you allowed only 12 digits, for example, after a while, and it goes very fast, after a while, the changes are only in the 13th or 15th digits. So on the screen, you see the same number. So that's a safe point to stop, and you say that this is approximately the root. Okay? So let us now see what program we will write for the computer. So you see the only formula is here. This is the technical part. This is where calculus comes in. Okay? So the other part, you see, geometrically, we don't see any calculus, because you are drawing a tangent line. We think it's geometry, but the equation of the tangent line is calculus, because it says that the slope of this line is the derivative of the function at that point. Okay, so let's do that now. So the equation for the tangent line to y equals f of x at x sub 0 f of x sub 0. Okay, so slope is, so this is f prime x sub 0. So this is where we use calculus. Okay, therefore equation is y minus f of x sub 0. Okay, so it passes through this point, equals the slope is this, and it passes through this point. Okay, so we want to find where this line intersects x-axis, that is where y is equal to 0. Okay, so we want to find the point where this tangent intersects x-axis. That is, solve for x when y is equal to 0. Okay, so this is what we want to do. We translate it to calculus. We find this. Okay, so this is minus f of x sub 0, f prime x sub 0, x minus x sub 0. Okay, so I take this to the other side. I have f prime x sub 0 times x sub 0 minus f of x sub 0 is equal to f prime x sub 0 x. Okay, so I just took this to the other side. So at this point, I realized that in this picture, when I was drawing this, I was hoping that the tangent line is not parallel to the x-axis. Okay, if, for example, if I make my first choice here the tangent line is parallel to x-axis, and it will never intersect. Okay, so here algebra reminds me that if the tangent line is parallel to x-axis, f prime x sub 0 will be 0, and there will be no solution. Okay, so when f prime x sub 0 is different than 0, I divide both sides by f prime x sub 0. So I'll have this thing, x sub 0 minus f prime f of x sub 0. I'm dividing this now with f prime x sub 0. Okay, so this is my next guess. Okay, so now I have a formula. So in other words, first make a healthy guess x sub 0, then xn plus 1, the next guess will be the previous guess minus f of xn over f prime xn. Okay, so let me see what else I want to say about here. Okay, then I have calculations. Okay, so if you are lucky, okay, this sequence x sub 0, x1, x2, etc. converges to a root, because it may have different roots. We don't know where it converges to a root of y equals f of x. Of course, you can stop somewhere when you feel confident. So that approximates the root quite well. Now, of course, sometimes, as we see in the picture, if you choose an unlucky point, the sequence will never converge. In some cases, the graph may be such that, and you choose such a bad point, that this equation here takes you somewhere else. Here, the equation takes you here. So you oscillate back and forth, and you never reach that root. It never converges anywhere. Sometimes the shape is like this locally, but somehow, instead of making that lucky x sub 0 guess, you move a little bit to the right. And in that case, the tangent line cuts the curve at some other point, and then it converges to a different root. Okay, so you have to be careful with these things when you are doing numerical calculations. Of course, there's a big industry behind this. Under which conditions, on which intervals a first guess will converge to a root. Okay, so we don't want to do those things, but if you are interested, you should be prepared that and there are conditions about the behavior of the first derivative around an expected root. Okay, so that tells you if this thing sequence will converge or not. But overall, you can say this. If this sequence converges at all, it converges to a root. It may not converge to the root you had in mind at the beginning. It may suddenly jump around and go and converge to some other point. But if it converges to a root. Otherwise, if this first choice is bad, or if the derivative of the function is changing a lot, it will not converge to anywhere. Okay, so let's see some numerical examples. Of course, these examples cannot be done by hand, so you don't ask these in the exam. However, it is nice to know that there are some numerical ways. So, for example, we know, but maybe you don't know, there is no algorithm, finite algorithm, to find the root of a general fifth-degree polynomial. Okay, so there are algorithms to find roots of polynomials of degree up to and including 4, even though some algorithms are complicated, there are algorithms, and it is proved that we know for certain that there is not a single finite algorithm which will algebraically give you the root of any polynomial. Well, given a polynomial, if it is spatial, if its degree is 10, 20, it doesn't matter. If it's spatial, sometimes you can find the root. But when we say there is no algorithm to solve these things, we mean that you write an algorithm without looking at the polynomial. Then no matter which polynomial you take, you give it to this algorithm. And after finitely many steps, it will give you roots. We even relax this condition. We say that after finitely many steps, it will give me a candidate, a set of numbers which are candidates for roots. Even that is not possible. Okay, so it is proven that it's not possible. But fortunately, we have numerical methods. So here is a fifth-degree polynomial whose root we are trying to understand. We want to find one root. So examples. 1, f of x is x to the 5 plus x to the 4 minus x cubed plus x minus 1. Find a root numerically using Newton's method. Okay, so there are also techniques of understanding. Most of the time it works. Given a polynomial, is it one of those polynomials whose roots you can find algebraically or not? It has to do with Galois groups. I'm mentioning this name so that if you are interested, you know what to look up. Okay. So now here, you plot the graph of this roughly, and you see that the root is somewhere near, there is a root near 1. Okay, so you start making a guess. I think my first guess was x sub 0 equals 1. Then at x5, I found the following thing, 0.79 Okay, so this is how much Maple will display. Of course, this is not precise, then it's continuous, but Maple doesn't show this. Now, x6 is exactly the same, x7 is exactly the same, so it means that all the changes are on this side, so I can take it safely as a solution. Okay, so the sequence stabilizes after this. So here stabilizes, I'm using this in the sense that the screen of the software keeps showing the same number, the same digits. Okay, because generally the software is planned so that it calculates a few more numbers here so that it approximates this one. Okay, so these things are not changing apparently. So in fact, you check f of x5. And this thing turns out to be approximately 10 to the minus 10. Okay? Well, for all practical purposes, it is 0. If you are doing numerical calculations, this is numerically 0. Okay? So it works. Okay, so let's do another thing. So for example, we can calculate numerically pi. How can we calculate pi? You find an equation whose solution is pi. Okay, one of the easiest things is maybe cosine. Okay, so cosine will be 0 at pi over 2. So instead of cosine x, if you look at cosine 2x, right, then it will be it will give you something. No, if you look at cosine x over 2, okay, then if x is pi, you will have a 0. Okay, so second, calculate pi numerically using Newton's method. Okay, so every time you find a new method, digits of pi is one of the things that you check your program against. So this is one of the benchmarks. So let us check Newton's method against this. Of course, we'll be humble. We'll only calculate so many digits. Okay. Let f of x equals cosine x over 2. Okay, so we know x equals pi is a solution. Okay, so I think I again began with x equals 1. Okay, so let x sub 0 equals 1, then x4 stabilizes at this 3.14, the usual pi number, 9265. Okay, so this is according to that many digits. This agrees with pi. So this agrees with pi in this within this limits, within these precision limits. Okay, so again, you stop here because now x5 is precisely the same number, x6 is precisely the same number, so you stop the program there. Okay, so of course you can go back to the program and say in Maple, for example, you write let digits be 20, and then everything will be calculated according to 20 digit precision. Then you can keep this program running, and I don't know, maybe Newton's method converges very fast, so probably at x7 or x8 you'll get 20 digit precision. The number will be the same after that. Okay, so there is another thing, another interesting thing. So I think this computer scientists find this interesting. You can do division by using only multiplication, using Newton's method. Okay, so let us do that one. Okay, so let f of x equals 1 over x minus a. So you choose a number, a. Okay, so clearly the solution is x equals 1 over a. X equals 1 over a. Okay, so this is just a game. Instead of dividing 1 by a, we will find a method which will approximate a by just doing multiplication. So let's see how it works. So in these examples, I didn't write the equation of the tangent line, but I'll leave it to you. So let's do the equation of the tangent line here because this is interesting. So here, f prime x is equal to minus 1 over x squared, right? So we have xn plus 1 is equal to xn minus f of x. So where was the formula? So let me write the formula here. In general, xn plus 1 is xn minus f of xn divided by f prime xn. Okay. So this, you remember this formula through the fact that if the derivative is 0 at that point, the tangent line is horizontal, and the tangent line never intersects x-axis. So the formula should remind you there. So I sometimes get confused whether this f prime was here or here. Okay, so it should be in the denominator so that it will not allow me to divide by 0. Okay, so f of x is 1 over xn minus a over this thing, 1 minus xn squared. Okay. You simplify this. You get xn plus 1 equals 2xn minus a xn squared. Okay. So this means you can approximate 1 over a by doing multiplication only. Okay. So you can do division approximately, of course, by only using multiplication. Okay. So, for example, the most famous reciprocal is 7, 1 over 7. Okay. So let a equals 7 and make a choice. We know the reciprocal of 7, it is 0.14 something. Okay, so you make your first choice 0.1. Okay, because we know 1 over 7 is equal to 0.142857 and we have this notation meaning that this block repeats. Okay, so we help in this when you are using Newton's method, you have to help the method. Okay, so you have to find a healthy first choice so that the sequence will converge to the right number. So this is a nice approximation for this, and x5 gives you immediately this. Then x5 is correct, 0.142857, and apparently at this point I was doing some other calculations, so 2, 4, 6, 8, 10, 12. So I changed the precision to 12 there. Okay, so the others were small precision. So you see this, for all practical purposes, as I say, if you need a number, it means that you will take that number and plug it into some other machine. That other machine does not accept an infinite decimal expansion. So whatever, how many digits the other machine accepts, say 12. Okay, so if you calculate this thing up to 12-digit precision, you are done. And how do you know that this is correct, up to 12 digits? Well, you can never be 100% sure, but for almost practical purposes, if the next 6 or 7 numbers are the same, then you can say, okay, I'll take it for granted. But it's not correct. Okay, there are cases where this, if the computer is calculating 50 more digits, there are cases that this may change. Okay, so next semester we will look at, for example, summation of the reciprocals of integers. Okay, 1/2 plus 1/3 plus 1/4. If you do it on a computer, empirically, you will always be convinced that it converges to some number. You will start suspecting that something fishy is going on, because if your friend has a computer, or if he sets his software to digits 20, he will get a different number than you do, because that sequence goes to infinity. Okay? It goes to infinity very, very slowly, incredibly slowly, so a computer never catches that. After a while, the numbers that are adding are all here, and the computer doesn't see them, so the computer your software stops there. But these small things eventually make this digit one more. Okay, 2,000 years later, it will make this digit one more. Okay, infinity is a long time. So eventually, this number grows and grows and grows. Okay, so that's why we have all these theories. There are very strange counterexamples where empirical data points in one direction, but then if you dig to the bottom of this, you find something else. Okay, fortunately that happens, because then you discover something about universe. Okay, so this was about reciprocals. Okay, so another thing is, now there is something called fixed point, which is very important in scientific calculations. So fixed point is a point where the y equals x line intersects your graph. Okay, so fixed points. Okay, A is a number. Okay, so this is italic A, this is Roman A. A is a fixed point for y equals f of x, or the function x, if f of a is equal to a. Okay, so find fixed points of cosine x. Okay, so let's see what we can do here. So the problem here will be something like this. Okay, so cosine x at x equals 0 is 1. So cosine x is something like this. This is y equals cosine x. This is y equals x. So this point, So this point is, say, x because it is on yx, but it is also, since it is on this curve, it is x cosine x. Okay, so this is a fixed point. This gives a fixed point. Okay, so we can solve it using, we can approximate that numerically using Newton's method. Okay, so using Newton's method, we can numerically approximate this point using the following function. Using the function y equals f of x, which we define as cosine x minus x. Okay? So if you find the zeros of this, it will give you this point. Okay? So again, I start with, here I write I start because you can start at some other point. A healthy choice would be to plot this and make it larger and larger, and then on the screen you get an approximate value for this point. You start with that point. So I started with x sub 0 equals 0.1. Okay, so let us write the graph of this. So this is the graph of the tangent line. But of course, I'm not writing the graph of tangent line now. We are writing the graph of something else. We are writing the graph of cosine x minus x. So it will go like this down, and it will go like this, and here it will cross the x-axis. F prime x is equal to minus sine x minus 1. So xn plus 1 is equal to xn minus cosine xn minus xn over, okay, let me keep the minuses here. You can simplify this later, minus 1. Okay, so you iterate this. In my calculations, x5 gave a stabilizing point. So after this point, I have these huge digits. So let me just write it for fun. Okay, you calculate cosine at this point. Of course, everything is in radians. Where do we use radians? We use radians here. Okay, when you take the derivative of cosine, it is 1 times minus sine x. Okay, so that's where you use radians. If it was, neresi zero olacak? 0.1. Yes, 0.7. Okay. Okay, so when we talk about fixed points, there is another method to find this fixed point, a very cheap point. You make a guess. Okay. Well, here, if you know that this is around 0.7, you can start with 0.7, but it doesn't matter. If you are lucky, 0.1 will also do. So you press your calculator cosine button, calculates you 0.1 and gives you a number. Then you press cosine button again, calculates this cosine of the second number. Okay, so you keep pressing the cosine button on your calculator. After a while, the numbers on the screen don't change. It means that the change is somewhere else, and the software is not seeing it. Okay, so that number, that's the number stabilizing on your screen, will be this number. Okay, so let's see why it works that way. Again, it's just like Newton's method. There's a huge industry behind this, telling you when it will work, when it will not work, how much precision you may expect, etc. Okay, but we are doing this just to entertain ourselves. Okay, so this brings us to Picard's method for finding fixed points. Okay, so that is solve for f of x equals x. Okay, so here to understand the method, again we draw something. Okay, so let me draw an ideal situation. Okay, so that's why we have so many methods in scientific and engineering calculations, because some methods solve certain problems, but they are not good in some other problems, and there you invent other things. We are not looking for a unified theory of mathematics. If you can solve something, you are happy with it. Okay, so the right-hand side is y equals x, so let us also draw it like this. So this is y equals x. So we are trying to find the point where y equals f of x intersects this. Okay, so the graph, so let me draw this like this because, okay, so this is y equals f of x. So again, this is the fixed point. So this is the point x, x, and also x, f of x. So x equals f of x. So this is the point we are trying to find, to approximate. Okay, so here you do the following. You make a guess. Okay, so you make this guess, say x sub 0, and then you go and calculate this point, which is x sub 0, f of x sub 0. And then you consider this just like a billiard board, okay, but somehow the reflections are like this. Okay, so it goes here. Okay, you calculate this point. So this point is, what is this point? You see that here y component is f of x sub 0. Okay, so here y and x components are the same. So this is f of x sub 0, f of x sub 0. So this is your second choice. This is x1. Now you repeat. Repeat means that you take this as your choice. You go up to the graph. Okay, you calculate this number. This is x1. Note that x1 is f of x sub 0 now. Okay, because I took the x coordinate. You calculate this point on the graph. Then you go like this, and you calculate this point, f of x1, f of x1. Okay, and now this is your next choice. x2. Your next choice. Keep going. Okay, so in the figure, you will be convinced that this thing is squeezed between these two graphs. It oscillates there very fast to the solution. Okay, so again, you see that it works because I chose the slope of my curve like this. Okay, so there is a bound between there is a bound where if the slope of the curve is between those bounds, then this thing will converge. If it is too bad, it may oscillate. It will never converge. Again, the overall summary is that you can blindly apply this theory. If it converges to a fixed point. Okay? Since the graph is a huge thing, it may converge to some other fixed point, but if it converges, the point is a fixed point. Okay? So, so this works most of the time. Conversely, you can use Picard's method to find roots also. Okay, so sometimes it's easier to push buttons. So let me also mention that. So you see we use Newton's method to solve a problem of Picard. Now we can use Picard's method to solve a problem of Newton, because all you have to do is add and subtract something. Okay. So we can use Picard's method to find roots for f of x equals 0. How can you do that? Any guesses? We have to find, Picard's method is you have to find a function and find its fixed points. Now we have this function. We want to find its roots. How can I change this into a fixed point problem? According to Picard's method, I must have x on the right-hand side. Mathematics is very easy. If you want something, you write it, okay? And then you say, what should I pay for this, okay? It's just like going to a bakkal. First you get your gazoz, and then you say, how much was it? Okay, so I want to write x to the right-hand side. I write there. Okay, so now how much do you want for this? If you write x to the right-hand side and you still want equality, you must write left on the left-hand side, x also, okay? So, okay? So take this as your g of x as g of x and find fixed points of g of x. Okay? So I keep telling you, mathematics is easy. Nobody believes me. Okay, so well, we can, for example, play the same thing here. So, for example, use Picard's method to find fixed points of cosine x over 2. Okay? Use, so g of x equals cosine x over 2 plus x. Okay? When x is equal to pi, this will be 0, this will be pi, it will be equal to x. Okay? So fixed points of this. This is pi. So if you iterate this, if you just write one-line program and keep it running, okay, so what do? We say let A equal this, and then repeat. Okay, so then this new thing will be x, etc. And eventually, you stop the program at some point when you see the same numbers repeating on the board, and that's a respectable approximation for pi. Okay, so let us do something a little bit more serious with Newton's method. Okay, since this is very serious, let me do it in purple. Okay, find the absolute minimum of the function f of x equals x to the 6 minus x to the 4 plus 3x cubed minus 2x. Okay, so you see that it is hopeless to do it by hand because you'll take the derivative, equate to 0, but stop there. The derivative is a fifth-degree polynomial, and it doesn't look like any special polynomial, so you won't be able to algebraically solve it. So our only hope is to numerically find critical points, okay? And then going back to calculus, calculus says that one of these is, well, all of these are probably local minima and local maxima, if not inflection point. Okay. Now, this even degree polynomial, so the graph comes from plus infinity, does something here, and then goes to plus infinity again. So somewhere in between, it has an absolute minimum. Okay, so we are trying to find that point. So you plot the graph using a software. Well, I don't have to mention this because you can't do this by hand. Plot the graph. When you first plot the graph, if you just say plot this with respect to x, you'll get something like this. Okay? So you understand that it is too rough. You start giving small numbers plotted. So again, what I did was plot it between minus 2 and 1. Okay? So more specifically, the graph is something like this. So let me see. It comes like this, goes like this. Obviously, 0 is the solution. So it passes from here and here. Okay? And on the graph, you notice that this is minus 1.5. And somewhere you have minus 1. Okay? And on the graph, you also have numbers corresponding to this. So you see that this is the global minimum. This point gives the global minimum. Okay? So the corresponding x here, so let us say A here. A. So A is a solution of f prime x. Okay? So you write f prime x is equal to 6x to the power 5 minus 4x cubed plus 9x squared minus 2. Okay? Take this as g of x. Consider Newton's method for g of x equals 0. Okay, so you will have xn plus 1 equals xn minus g of xn over g prime of xn. So you'll take the derivative of this once more. Okay. By looking at the figure, by looking at the graph, you can take x sub 0 as one of those things. Let me see, I took x sub 0. Well, I didn't write it, but okay, I took this one for some reason, minus 1.5. You can take minus 1. Okay. You just make a choice around this one. You don't know precisely where this is. Okay, so on the graph, you read a number. Okay, so it doesn't matter what number you read because you just give it to the software. So I made this initial choice, and everything stabilized after the 6th step. Okay, at 6, I got minus 1.29, 3227442230, and on the computer, it was like they were all the same on the software. Okay. So this is a root of, numerically, this is a root of the derivative. So conclusion, x6, f of x6 is minus 2.02 something. Okay, so I have all these numbers here. It is the absolute minimum of this function. Okay, so here, now that I wrote all these numbers, maybe I should 32, 23, 57, 627. Okay, so that's how much, that's what the software showed me. Okay, so this is a serious way of using Newton's method. Okay, because the question is to find the absolute minimum. Okay, so this is, you see, almost precise. Okay, so you can take that number as the absolute minimum of this thing. Here we use Newton's method in finding roots of the derivative. Okay, so what does the general rule says? Take the derivative, equate that to 0. Okay, so that's the bottleneck in all calculus problems. After equating to 0, solving the equation. Okay, so that's why in all the exam questions or in the exercises, the derivative is either quadratic or is a cubic but with an obvious root, so that after you divide by x minus that root, you get a quadratic again. But in real life, you have to find numerical solutions. Newton's method is one of the solutions. This is not the best method, but this is the most complicated method we can discuss using calculus. Okay? Later on, if you take analysis courses, there are much more complicated and faster methods. Okay, let's take a break, and we'll continue after the break.